When you manage a massive cluster of jobs, even a minor system hiccup can be catastrophically expensive. While many focus on software optimization, the physical limitations of our electrical grids have become the ultimate constraint for high-performance computing. Securing gigawatt-scale power feeds is now the first and most critical step in standing up modern clusters.
Data and electricity into these things called data centers. Now, by 2028, the expectation is this is going to suck up to 50 gigawatts of power. Now, for reference, picture lighting up all of New York City twice. That's how much energy is being consumed. It is estimated they're going to spend up to $3 trillion by the end of this decade alone. This is a huge arms race to scaling superintelligence. And there's one company in particular that we're probably going to be highlighting a lot throughout this episode, just because they've been absolutely
Without a stable, massive power infrastructure, even the most advanced computing architecture remains completely useless. Modern platforms face a highly chaotic landscape where compute demand spikes instantly and unpredictably. This forces infrastructure teams to provision isolated environments in seconds rather than weeks.
GPU clusters are exploding, compute demand is no longer predictable, nobody really knows how much they need, what they need, and everything is chaotic. So platform teams are expected to deliver production-like environments in seconds, not weeks. So tonight, I really do believe we have the perfect trio to help me talk about this. So right on my right, I have Felipe.
When thousands of workloads hit simultaneously, traditional scheduling layers are pushed to their absolute limits. Operating a massive cluster of high-performance chips means that a single configuration error can bring down the entire system. At this scale, downtime is measured in millions of dollars of lost capital.
Like there's one of the people that we talk with they manage a large GPU based farm, and they measure everything in terms of minutes of GPU downtime, and it's always millions of minutes because they have lots of GPUs. So if they have an issue, whether it's during a training run or whether they're sort of doing pre-training processing or doing anything, if there's a hiccup, like if somebody fat-fingered a file.
When hardware is this expensive, maintaining high uptime is not just a network, it is the core business driver. As GPU clusters scale to tens of thousands of nodes, hardware component failures become an hourly event. This constant instability forces training jobs to frequently halt and restart from save checkpoints.
Now, during this whole training phase, there could be intermittent failures, often from the hardware components involved into the training. So whenever there is a failure, the job has to be interrupted and it has to restart. And it does so by leveraging the most recent checkpoint that it produces along the way. So as we noticed, the job is started many times during the lifespan.
Minimizing restart overhead is a non-stop battle against entropy to keep large-scale model training from stalling. Pushing clusters to achieve massive computing milestones requires staggering amounts of electricity. If the physical power delivery and cooling systems cannot cope, the hardware is forced to throttle.
The biggest problem is power. So even Tsubame, or machine Tsubame, is doing pretty well now. Compared to Blue Gene, probably about half as efficient, but because of some of the early acceleration attempts we had with ClearSpeed, we're doing very good. However, in order to attain 10 times performance boost in terms of power performance, and maybe 1,000 times over 10 years, we have to do much better than a more.
The scaling bottleneck has shifted from a silicon problem to a physical infrastructure limit. In large distributed environments, computing speed is heavily limited by the network interconnects. If the network lacks the bandwidth to move memory states quickly, processing units sit idle. Clip file 6 MP4, 00 seconds, 2240 seconds.
And scale across data centers. I believe in Ethernet so much that I carry this Ethernet cable in my pocket today to show you something as simple as this is the only way you can build a machine learning cluster that's large enough. By the way, it's very easy to find somebody who can work on Ethernet technologies. Very hard to find somebody who's going to work on all these other esoteric technologies that people have pitched as the way to build machine learning clusters.
Network performance directly determines whether adding more nodes actually speeds up your calculations. Pushing higher data rates over physical links is running into severe material limitations. Copper interconnects face steep signal degradation over longer distances, forcing a massive push toward advance. Cabling.
That it needs. So today, these platforms are starting to push 224 gigs per differential pair, which is the data rate that you can do through these interconnects. So when you have a chip like NVIDIA's and it has NVLink and it wants to connect at the highest speed that copper lets you, most of the interconnect today is 224 gig. So that's where we're at today. But then you always have the
At extreme frequencies, physical materials dictate the boundary lines of how large a cluster can physically grow. When a distributed model runs into an error, tracing the issue across thousands of nodes is incredibly tedious. Without specialized data tracing on telemetry tools, debugging scale-up systems is practically impossible.
That metrics is trending down. Yeah. So since we run so many models at a given point in time, it's kind of difficult to first pinpoint which one. Yeah. Then when we can pinpoint it, like production models, they end up with a pipeline where data gets processed, signal gets processed, gets aggregated, and then there's multiple phases. Yeah. And figuring out which phase is actually causing the problem is really difficult. Exactly. Something it's like
developer velocity at scale is directly linked to the maturity of your diagnostic and telemetry tools. Relying entirely on on-demand scaling is a risky strategy when specialized hardware is highly scarce. Infrastructure teams must carefully balance resource availability against idle hosting costs.
One of the promises of Kubernetes is scalability on demand, being able to access the resources only when you need them. And that worked great when those resources were only CPU and memory. But now with GPUs, which are hard to get, you are faced with the challenge of, do I actually pre-provision them and pay for them even if I'm not using them? Or do I auto-scale and then risk not having them available? So I think obtainability, generally speaking, is one of the biggest challenges that people are going to face, especially making sure it makes sense from a cost.
Securing predictable access to hardware remains a critical challenge for modern distributed runtimes. The physical limits of transistor density are forcing us away from single-chip performance leaps. Scaling now requires highly complex, multi-node cluster synchronization.
In this episode, Tim argues that we are hitting diminishing returns and running into hard physical constraints, while Dan argues that we are still leaving huge performance on the table and that today's models are lagging indicators of hardware progress. Then we shift into a fun, practical discussion on how to use agents and what to expect from AI in 2026. Please enjoy this fun conversation with Tim and Dan. Tim and Dan, welcome.
Thanks for having us.
So, Tim, a few weeks ago, you wrote a great provocative blog post entitled
Single Node Performance is no longer the metric that matters. The network is the new computer. Managing a modern cluster requires coordinating a massive, highly fragmented software and driver stack, ensuring compatibility from low-level drivers to high-level orchestrator S is a persistent challenge.
Clearly security, because the message is you need to make sure this is secure, and the foundational security practices that you've been doing within your IT management stack already, they still exist, but now you need to layer in the fundamental components of security for AI, right? So how are you going to protect the LLM? How are you going to enable guardrails? How are you going to protect the embeddings, the inputs, the outputs, right? Not necessarily focused.
Single driver mismatch can ripple through a cluster and cause widespread operational failures. Traditional computer bankmaker relied on simple, deterministic metrics, but assessing probabilistic models requires an entirely new framework of subjective and interpretability testing.
Benchmarking, as I said in my introduction, the reality is that benchmarks, were pretty stable for quite a long time and gave people a very consistent and straightforward way of comparing systems and making decisions. But with the pace of change in AI and the complexity of these new stacks, it looks as if the old model might not fit quite as neatly. I wonder if you could start by giving us a perspective on what is different now, and what does that mean how do we need to
Understanding the inner reasoning of complex systems is the next frontier in quality assurance. Renting massive clusters by the hour on public cloud platforms quickly becomes cost prohibitive. Teams must implement highly dynamic, auto-scaling policies to keep waste to a minimum.
Release of ChatGPT, so it was a good way to go more and more on this area.
Yes.
So we got at the moment, I don't know, something between 80 to 90% of our demand for AI rather than HPC or 3D rendering, what we got at the beginning.
Okay, so you started with the 3D rendering, which was more around gaming, and that's NVIDIA as well, is it? Or
Yeah, more or less, because we decide to aggregate.
Resource efficiency is no longer just an engineering goal. It is a critical financial necessity. The sheer cost of scaling large-scale compute blocks has created a deep division between well-funded industrial labs and academic researchers.
Very short, what I realized doing that is machine learning is incredibly computationally expensive. It just requires loads of, at the time, GPUs and still kind of predominantly GPUs. And as a relatively poor PhD student, I had about 4 of them that I could run my research on. And the big players were doing similar models and similar kind of explorations with thousands of them. And they'd run these things for weeks at a time. And what stuck with me from that was the realization that I had everything else I needed to do these experiments. I knew how to do them. I had the data. I just didn't have the compute. And
when access to computing power is restricted, the pace of independent research inevitably slows. When different teams deploy siloed applications across multiple clouds, enterprises face massive security risks. This lack of centralized tracking creates a governance nightmare.
Amazed at the pace at which the number of use cases.
Establishing a centralized, secure control plane is essential to protecting sensitive enterprise data. Capital expenditure in hardware infrastructure has reached historic heights. Hyperscalers are spending hundreds of billions of dollars to build out custom, high-speed architectures.
Today's number is $400 billion. That's how much money just the 4 hyperscalers, Microsoft, Amazon, Meta, and Alphabet are spending or expected to spend in this year alone. For context, that's more than 15 times the Manhattan Project, 2 times the amount of money it took for us to do Apollo program, which literally put the man on the moon. And that number could globally reach $3 trillion. We are arguably in one of the most...
This massive capital cycle is a direct response to the absolute necessity for faster, scaled-up compute. Deploying a supercluster with over 100,000 nodes requires a monumental effort in physical logistics and infrastructure design. Clip Fidget's Figispians 51 for 7120.
100,000 GPUs was built in only 122 days. And just to give you some frame of reference, the largest exascale supercomputers only have a fraction, maybe half to a quarter as many GPUs as XAI has here, And yet, those deployments generally take many years from start to finish. The engineering accomplishment here is absolutely amazing, and there's work still being done. But I thought, let's go take a look at
liquid cooling systems, high-speed networks, and massive power delivery must be orchestrated down to the millimeter to succeed. Running graphically intensive environments over remote connections often introduces heavy latency, offloading these graphics processing tasks to a shared virtual hardware layer is key. Clip fed in Ovipria, 438060 for 48.
And so vGPU is NVIDIA's solution to the problem that CPU-only VMs have. It allows for the sharing of GPU resources to the VMs to allow for the graphics or hardware acceleration part of it to be offloaded onto the GPU. Usually in VDI, there's just the server hypervisor and the VM and the thin clients that they log in with. With vGPU software, you can have the server, NVIDIA support.
Dynamically allocating virtual GPU slices ensures high-quality remote performance and maximum node utilization. Shifting workloads from batch training to real-time distributed inference introduces massive network coordination challenges. Clip Vidsmet, Fakoli 12240, 14344.
Because over the last year, it became obvious to everyone, basically, that now it's not just the engineering problem of placing the things somewhere so that they run, but it's the real AI infrastructure challenge, the one which is moving the infrastructure decisions, the one which is deriving the state-of-the-art solutions. And challenges are plenty in this domain. Performance.
Abstracting cluster management allows developers to scale their services globally without managing raw servers. Managing advanced workloads requires scheduler frameworks that understand physical hardware layouts. Simple, count-based scheduling often leads to node starvation and performance drops.
And at the heart of this revolution are GPUs and the platform that provides applications access to them. For many, Kubernetes has already become this platform. But we still have a lot of work to do before we can unlock the full potential of GPUs to accelerate AI workloads on Kubernetes. This includes changes to both the low-level mechanisms used to request access to GPUs, as well as the higher-level processes needed to map a set of GPUs to a workload based on a
Schedulers must map jobs directly to the physical topology of the cluster to minimize network latency, translating algorithms into highly parallelized styles GPU. Instructions can be exceptionally difficult, often requiring low-level code rewrites.
Not free, you still have to buy your hardware. But when you go to GPU, now you have to think differently. You probably have a higher latency when you do this computation. Things have to ship over the PCI Express to the GPU and back. There's higher latency. But you may get more throughput, so that may be a good trade-off. But complexity definitely increases. You have to change your programming model. GPU doesn't execute like your CPU. You have to rethink the problem.
High-level compilation tools allow developers to maintain simple code structures while running at maximum hardware speed. Platform teams are increasingly adopting composable infrastructure templates. This allows developers to self-service the exact resources they need without getting bogged down in infrastructure setup.
Culture team back in September when we excitingly announced our partnership with AMD to take to market their Instinct GPU, the MI300X. And since we announced the MI300X, we are now have also announced the Instinct MI325X. And soon, in June, we'll be announcing even the latest generation of GPUs, so stay tuned for that. But I actually misspoke because actually we've been a long-standing partner for AMD.
Giving developers propagate secure resources dramatically increases deployment speeds and eliminates operational bottlenecks. Training state-of-the-art models requires coordinating memory across thousands of nodes. The sheer memory footprint of modern parameters presents a massive serialization challenge.
The past few years, there's these models called transformers that really do well in understanding human language and text. However, they have a lot of parameters. And so if we look at the number of parameters in these models over the past several years, we can see that they are growing exponentially. So this y-axis you can see is logarithmic. So this is an exponential growth in the number of parameters in these language models. Way back in 2018, we started at about the same size as state-of-the-art vision models, but we've grown exponentially since then.
Successfully managing this memory state requires a highly optimized combination of model and date, a parallelism, orchestrating machine learning pipelines across distributed clusters requires unified runtime frameworks. Developers need a straightforward way to scale their code without worrying about server provisioning.
And our mission is to make scalable compute for AI and ML in Python really easy and super straightforward to use. And we do it because scaling is a necessity and scaling is hard, but we want to make it as easy and simple as possible for everyone. So yeah, just a quick overview of the agenda. So we are going to go over the state.
Standardizing the software stack is the only way to make large-scale compute resources easily accessible to development teams. Migrating training scripts from single-node to multi-GPU setups requires specific configurations. You must ensure that each worker process receives unique data subsets to avoid overlapping.
GPUs. Typically, each GPU runs one process, and setting up a group is necessary so that all the processes can discover and communicate with each other. So I'm going to write a small function that takes in two arguments, the rank and world size. The world size is the total number of processes in a group, and the rank is a unique identifier that is assigned to each process. So it usually ranges from 0 to world size -1. So in this function, I'm going to set
wrapping standard PyTorch scripts in distributed parallel wrappers is essential for reliable process communication. Due to physical constraints in space and local power grids, large GPU clusters are increasingly being distributed across multiple geographic regions.
Because no longer you can hold GPU clusters that need to do AI workloads, whether it is ingest for training or it is for inferencing, now has to be geographically distributed because of power, because of space, because of all the other challenges. And that scaling model is interesting because networking and network connectivity becomes critical and core, like what you mentioned.
This geographic split shifts the scaling bottleneck from raw local compute to highly complex, low-latency one routing, fusing conventional processing with accelerated computing is the only way to scale beyond traditional physics boundaries. We must coordinate hundreds of thousands of chips as a unified fabric.
Beyond Moore's law. The AI
The scaling frontier is no longer about faster individual cores. It is about perfect cluster-level orchestration. Running massive workloads requires purchasing highly specialized, extremely expensive hardware. Maximizing utilization of these systems is a critical priority for enterprise budgets.
Need a cost efficiency. Cost efficiency involves the GPU utilization, and GPUs can be very expensive. We want to make sure that we are doing optimum GPU utilization. That way, we don't waste the resources. We can concurrently handle multiple requests. That way, we can do cost efficiency. Now, let's take CAP theorem. In this, more than consistency, we want the system to be available and be able to tolerate the partitions. That is why we will take a
Finding a path to lower costs and higher efficiency is the only way to justify the astronomical budgets of modern data centers. Geopolitical tensions and strict compliance regulations are forcing many international organizations to build Independent, localized AI clouds. Clip 5F7WHVT270Q200 and 1770 6238-4.
However, I do think there will be the differentiating factor will be budget and hardware constraints. So I don't think the ideas will be proprietary, but the way or the resources that are needed to implement them. And so I don't see currently a take it all scenario where a winner takes it all. I can't see that at the moment.
Nathan, what do you think?
You see the labs put different energy into what they're trying to do, and I think to demarcate the point in time when
Deploying open weight models on secure, compliant regional infrastructure is crucial to maintaining data sovereignty. The competitive landscape is defined by a race to secure cutting-edge hardware, bringing massive supercomputing facilities online in record time requires a highly coordinated logistics pipeline. Clip Witz or Peterson 9560 11656.
Colossus 1. And there was. Colossus 1 was around 200,000 GPUs in size. Colossus 2 is over twice the size. We're talking about 550,000 GPUs. Now, for the listeners on this podcast, trying to understand what that means in perspective, 100,000 GPUs is probably the fastest supercomputer on the planet right now. So if you had 100,000 GPUs, you have the fastest supercomputer in the planet. But
the ability to rapidly procure, power, and cool these massive clusters is what defines the winners of the AI arms race. Single node performance is no longer the metric that matters. The network is the new computer.